Good afternoon, everyone. It's wonderful to see you here. I hope you had a great lunch and you're now full of energy for my talk. I'm Chaya Berezin Chaimson. I'm a full-stack developer and a tech lead in AT&T Israel R&D Center. And I have written code in a few different languages during my career, but my first and main love is Java. And that's why I'm so excited to be here today, not just because of my talk, but also for taking part in this first and awesome Java Summit in Israel. As I said, I'm a full-stack developer, and as so, I get great pleasure from seeing things working end-to-end and understanding all the different components in the system. And today, I'm going to talk about one special component in a distributed system and how it helped us address several challenges in our own system. So, it all started when our team got a request to develop a new product. And we went through these endless design meetings where we were thinking about the new system, design, and requirements. And in the end, we came to the following conclusions about our system architecture. To simplify, we will have a few client applications, few MVC and web applications, and we will have a few microservices implementing the backend logic and exposing the API to the client applications. We also knew that most of these microservices will be written in Java Spring Boot, as this was the team expertise and preference, but we didn't want to enforce it. We wanted to keep it flexible. We knew the team might expand, and we wanted to have that flexibility to choose a different technology stack for additional microservices. So our system will look something like this. Now, as lesson learned from previous project development, we wanted to address in this initial stage of architecture several challenges that we have faced in the past and caused us some real headaches. First, as we develop in Agile methodology, we know that requirements often change, and so architecture often changes. And we wanted to have a unified facade, a unified interface to our client applications that will encapsulate the internal microservices architecture and will give us the freedom to redesign and refactor our internal microservices without worrying about backward compatibility to the client applications. Second, we chose the architecture of microservices, and this architecture has lots of pros, but it has some cons as well. And one of them is related to cross-cutting concerns. Cross-cutting concerns are aspects that are common to all of the microservices. All the microservices has to handle them. And we knew we have some common aspects to all of our microservices that we want to handle in a unified way. For example, observability. We had to stand our specific organization standards of observability. For instance, we had a requirement to log all the requests and responses coming in and out of our system in the same specific manner according to our organization standards. Another common concern that we had was about the security of our system. We wanted to protect all of our APIs, so only authenticated and authorized users will be able to access them in the same way. And additionally, we also wanted to apply some resiliency patterns on all of our microservices. Now, of course, we could write a shared library with all the cross-cutting concerns implementation and force all the microservices to use it. But there are two problems with this approach. The first is enforcement. We need to enforce all microservices to use this shared library. And enforcement is not always easy, especially with large-scale teams. It doesn't always work as we expect. And the second issue is that, I'll remind you, we were not sure that all of our microservices will be written in the same technology. So we could not have a shared library that will also be technology agnostic. At this point, we understood that we needed to introduce a new guy into our system and implement the API gateway pattern. Now, anybody here heard about the API gateway pattern? Uses it? Raise your hand. Okay, good. So In short, API gateway is a pattern in distributed system design. And this pattern describes a new service to the system that provides a single entry point for a certain group of microservices. So if we go to our initial design, which looks like this, if we implement the API gateway pattern here, it will look like this. Here's an additional component in the middle called the gateway. And this component receives all the requests from the client applications and is responsible for sorting and routing the requests to the internal appropriate microservices. Having this component, the gateway component, as in the middle, functioning somewhat like a proxy, can solve all the challenges that I've stated before. It can provide a unified interface to the client and hide the internal microservices implementation. And we could also implement in this gateway component all the cross-cutting concerns that I've mentioned, the observability, security, and resiliency. With that in mind, we started to look for an API gateway implementation that will answer all those needs. And when we were looking for such an implementation, we also bear in mind that the gateway is right in the middle. We don't want it to be the system bottleneck. So we looked for an implementation that will also be fast and non-blocking and scalable, of course. Now, in the industry, there are two types of API gateway implementations. There are off-the-shelf products that we could take as is and configure the routing according to their documentation, maybe apply some customizations via plugins in Lua or something like this. But overall, it's a ready product that we could use as is. The other type of API gateway implementation is libraries that we could consume in our own application and customize it according to our own needs. Now, we didn't want to choose an off-the-shelf product because we had a requirement for some highly customized behavior that we wanted to implement. And we also wanted the developers to be able to implement this logic, and we wanted that it will be developer-friendly, so that it will be easy for the developers to inject some customized behavior in this gateway component. And furthermore, we wanted the developers to have the ownership and the responsibility for this gateway component. And these all are likely impossible, or at least very hard to achieve with an off-the-shelf product. So we decided to stick with library implementation. And after a thorough research, we came out with Spring implementation of the API gateway, which is Spring Cloud Gateway. Anybody here uses Spring Cloud Gateway? Raise your hand. So Cora, of course, and my teammates. And so good, you're in the good place. So Spring Cloud Gateway. Spring Cloud Gateway is an open source project built on top of the Spring ecosystem, which was very good for us as we were mainly Java developers. And in particular, it's built on top of Spring Webflux. And this is from their documentation. Spring Cloud Gateway aims to provide a simple yet effective way to route to APIs and provide cross-cutting concerns to them, such as security, monitoring of metrics, and resiliency. It sounds promising, right? It handles routing, it handles cross-cutting concerns, it's efficient, and we know it's built on top of Spring Webflux, which means it's built on top of a reactive stack, so it's non-blocking I/O. And indeed, from our experience so far, we found Spring Cloud Gateway a great solution. And I will scan here its main features and how we use them to tackle all the challenges that I've stated before. But first, let's start with explaining what Spring Cloud Gateway is and how it works. So Spring Cloud Gateway is a bare Spring Boot application with this only dependency of Spring Cloud Starter Gateway. And once we have this dependency in place, we can go on and define the gateway routes. Spring Cloud Gateway is just a definition of a list of routes. What is a route? If we go back to our architecture, a route is this. A route is the definition of a specific request that will be routed to a specific microservice, and the manipulations that this request and the response will pass in the way. Routing can be configured in Spring Cloud Gateway both programmatically and declaratively, and I will show here how to configure the routes in the application YAML, as I always prefer to keep the routing decisions in the configuration phase. So in application YAML, Spring Cloud Gateway routes, here we define the list of routes. A route consists of 3 elements. The first one is the target. The target is the destination URI that the gateway will route the request to. So it's done with a URI argument, and here I define the request to be routed to some local microservices on localhost port 9001. Now, we might want that to apply some manipulations on the request before it's routed to this target URI, or on the response when it returns from this target URI. And this is done by a well-known concept of filters. So we can define a set of filters on each route. Some filters are executed before the routing of the request, and these are called pre-filters. And here is an example of one of the gateway pre-filters. It's called strip prefix, and this filter strips the prefix of the request path. And some filters are executed on the response when it's returned from the target URI. And these are called post filters. And here's an example of one of the gateway post filters that adds a response header on the response. The response header name is color and the value is blue. Now, in order to complete the routing definition, we need to tell the gateway which request will match this route. We obviously don't want all the requests to match this route and to be routed to this specific microservice. So we have a list of routes, and we need a way to distinguish which request matches which route. And this is done using the third argument that's called predicates. And the predicates are Java 8 predicates that has the request as an input, and they determine whether this request matches this route. So here I use the simple gateway predicate that is called path. And this predicate determines that all the requests that starts with the /API/flights will be matched to this route. So if we have this route defined, it means that if the client application sends to the gateway a request with a prefix of /API/flights, the gateway will strip the prefix of the request and will forward it to the target URI, which is localhost 9001, right? And once the microservice returns the response, it passes through the gateway adds the additional response header, color blue, and return it to the client application. So a quick wrap-up. A route is a combination of a target URI, a list of filters, and a list of predicates. Now that we understand the basic building block of routes, we can go on and understand Spring Cloud Gateway architecture. Have a look at the diagram. We have the client application sending a request to our distributed system. The request first hits our Spring Cloud Gateway component. And in the gateway itself, there are several stages. The first stage is the gateway handler mapping. And this one is responsible for mapping the request to its appropriate route. And it does it by the list of predicates that are defined on all of our routes. So we saw the path predicate, but Spring Cloud Gateway has a list of predefined, ready predicates that we can use some more sophisticated predicates, and you can even go on and create your own customized predicate. Once the route is determined, the second stage is the gateway web handler, and this one builds the filter chain that the request will pass through. And each filter code is executed until the last filter, the proxy filter. This is the gateway system filter that proxies the request outside of the gateway to the destination URI. And once the destination URI returns a response, it's again processed through the chain of post filters until it returns back to the client application. once we understand this architecture and the terminology of routes, we can go on and examine how we tackled all the challenges that we have one by one using Spring Cloud Gateway. So, unified interface. We wanted to have a unified interface to our client applications that will hide the internal microservices implementation. And having this gateway component in the middle, exposing a list of routes, and in particular, the combination of the predicates plus the target URI results in a unified interface, because we can change the internal implementation as many times as we want, and it will affect the target URI of the routes. But as long as we don't change the predicates, the interface to the client's applications remains the same. It's totally transparent to the client applications. So unified interface is checked. Now, let's talk about the cross-cutting concerns. Once we understand the gateway architecture, it becomes clear to us that we can implement any cross-cutting concern that we want by using a gateway filter. So either use one of Spring Cloud Gateway ready filters, or create our own customized filter and implement there any logic that we want. Right? We can implement a logic in a filter, define it on specific routes or on all of our routes, and then all the requests will pass through this logic. So, for instance, observability, we talked about the logging. We wanted to log all the requests and responses, and we did it by creating our own logging filter with our own customized logic of logging according to our organization standards. And so all the requests and responses coming in to our system are being logged our way. Creating a customized filter in Spring Cloud Gateway is very simple. It's simply extending an abstract factory, overriding the apply method, and in the apply method, we return a gateway filter instance. And in this logic, we implement the pre-processing logic and the post-processing logic, and that's it. Now, the code here is a bit complex, polluted with mono and Flux, and this is due to the fact that Spring Cloud Gateway is built on top of Spring Web Flux, which means the code here uses Project Reactor. So this is just as a side note to your awareness. Okay, so observability is checked, and so any other cross-cutting concern that we want to handle. Now, let's talk about the security of our system. You could think that we could tackle security the same way as we did with observability. We could create our own security filter or authentication filter and implement the authentication logic of the authentication of our users. But the better news is that we didn't need to do it. Because Spring Cloud Gateway is built on top of the Spring ecosystem. It's just a bare Spring Web Flux application. It has full and fluent integration with Spring Security. So in our system, we use OpenID Connect and OAuth2 for authentication and authorization. And we've implemented it very easily with Spring Security in our Spring Cloud Gateway application. And this is very easy and very elegant. Actually, the same way as we would have implemented it in any other Spring Web Flux application. So we've tackled security as well. Now, I've got a few minutes left that I want to dedicate to resiliency. In distributed systems, we need to handle resiliency. We want to ensure that if we have a failure in one part of the system, we don't propagate it through the whole system. So the users will still be able to access to our system. And if possible, we should have a fallback behavior in place so the users will have a pleasant experience. The most basic implementation of resiliency is the retry pattern, which simply means that if we have a service that returns an error response, instead of propagating it right away to the client, we first try sending several additional requests to this service until it's hopefully available again and returns a successful response, and then we forward it to the client, and meanwhile the client is unaware to this temporary unavailability. the gateway component, as it's right in the middle, is the perfect place to implement the retry pattern between the client applications to the internal microservices. And indeed, Spring Cloud Gateway provides an out-of-the-box filter called the retry filter that we can configure like this in the application YAML. And then we can configure the how many retries we want to apply. We can configure on which request we want to apply this retry pattern according to the HTTP method or according to the statuses of the responses. And we can even go on and define the backoff policy of this retry, which simply means how many times the gateway will wait between one try to the other. So very useful. With just few lines of configuration, we have the first step of resiliency in place. Now, retry pattern is a great solution for temporary unavailability, but sometimes the service may be unavailable or unstable for a longer time, right? So after a few retries, it will still return an error response that we will eventually propagate to the client. For this case, there is another pattern, which is called circuit breaker pattern. And in short, this pattern examines the microservice stability. And after a few consistent failures, it decides that the microservice is not stable anymore, and it stops forwarding the request to the microservice, and instead it will apply some default behavior. So Spring Cloud Gateway, integrating with Resilience4j library, has a circuit breaker filter that we can use like this and configure the fallback URI argument. The fallback URI argument is the URI that the requests will be routed to in cases the circuit breaker is open, in cases the circuit breaker decides the microservice is not stable. Now, the interesting thing is that this fallback URI can be an internal gateway API. Since Spring Cloud Gateway is a Spring Boot application, it can have a REST controller and expose an internal API. And in this API, we could implement our default behavior for cases the circuit breaker is open. So either return some static response or perhaps the last response that we saved in the cache or anything else. So it's very powerful. Another interesting filter related to resiliency is the request rate limiter filter. The gateway, as it functions as the router of the request, can limit the request rate that will be forwarded to the internal microservice. Now, this is useful for preventing DDoS attacks, and it's also useful for cases that we have a service that cannot support a load above a specific threshold. So we better limit the request rate in the gateway component instead of forwarding it to the internal microservice and risking its availability. So again, it's very nice filter integrating with Redis, very useful for many applications. So we've tackled resiliency as well. To sum up, this was a rapid exploration, just the tip of the iceberg of Spring Cloud Gateway, and the tips and tricks from our usage and how it helped us address several challenges that I'm sure we are not the only one who face. I hope you now have a better sense of the importance of the API gateway in your distributed system architecture and a better understanding of Spring Cloud Gateway and its highly customizable and developer-friendly nature. These are my contact details. I'll be staying here for the rest of the day. So you're welcome to come with questions or share your experience. Thank you very, very much.